Good morning, students. In the last class, we discussed about electric field. Electric field due to a point charge is given by the equation E is equal to 1 by 4 pi epsilon 0 Q by R square. Electric field is a vector quantity and direction of electric field is always from positive Q to negative Q. Electric field is a vector quantity and the direction of electric field is always from positive Q to negative Q. Now, if there is only positive charge, the direction of electric field will be outward. If there is a negative charge, the direction of electric field will be into the charge. For example, positive Q. I draw the electric field line like this, directed outward, and it can extend up to infinity. Similarly, for a negative charge, the electric field lines can be drawn like this. It is coming from infinity towards the charge. We also know E is equal to F by Q. So from this expression, I can find the SI unit of electric field. SI unit of force is Newton and SI unit of charge is Coulomb. Therefore, SI unit of electric field is Newton per Coulomb. It also has one more SI unit, which is volt per meter. So SI unit of electric field is Newton per Coulomb or volt per meter. Now, to represent the electric field, I have drawn certain lines, and those lines are called electric field lines. In today's class, we are going to discuss what is electric field lines. Electric lines of force or electric field line is an imaginary straight or a curved path along which a unit positive charge is supposed to move when free to do so in an external field. Which means, if I place a positive charge, how that positive charge move in an external field, that will be the direction of the electric field lines. In simple statement, I can just say like this: it is an imaginary representation which shows the electric field due to a charge system. It is an imaginary representation which is used to show the electric field in a charge configuration. Now, see these two figures. The first figure shows the electric field due to a positive charge. Electric field lines due to a positive charge are directed outwards. That is what you are seeing in the first figure. Now, second figure. In the second figure, you can see all the arrows are coming inward. That is the electric field lines due to a negative charge. If we are taking a positive charge and a negative charge, look at the third figure. We are taking a positive charge and a negative charge. So, as I told, the direction of electric field is always from positive to negative. So, here you can see the lines of force are drawn from positive Q to negative Q. That shows the attraction force. Now look at fourth figure. There you have two like charges, plus Q and plus Q. So like charges will repel, and you can see here the electric field lines are getting repelled. And at the midpoint I have marked N, that N is called null point. That means it is the point where the electric field intensity is 0. Why it is 0? Because the electric field due to the positive charge on the top and the positive charge at the bottom, they both repel each other. So towards the center the intensity of the field decreases, and at the center point the intensity is 0, and that point is called null point. Now look at the fifth figure. This figure shows that you can see green lines, green parallel equally spaced lines. That shows uniform electric field. So if the electric field is uniform, the electric field lines are uniformly spaced parallel lines. Now let us study the properties of electric lines of force. The first thing, electric lines of force are imaginary lines. They are straight lines or curved lines, which we have seen before. Now the second point, a unit positive charge placed in the electric field tend to follow a path along the field line if it is free to do so. The third point, electric field lines of force emanate from a positive charge and terminate on a negative charge. That means electric field lines starts from positive Q and ends at negative Q. The fourth point, tangent to an electric field line at any point gives the direction of the electric field at that point. Look at the adjacent figure. The yellow curved line is actually the line of force. I have marked a point P, and at that point I have to find the electric field. So what I should do? Just draw a tangent, and that tangent gives the direction of the electric field at that point P. Now, fifth, two electric field lines can never cross each other. Why? Just look at that figure, adjacent figure. If two electric field lines cross each other, we already told tangent at any point gives the direction. So here you can see two yellow curves which shows the electric field lines. At that intersecting point, I can draw two tangents, which means electric field at that point of intersection is having two directions, which is not possible. So we can say electric field lines of force can never cross each other, because if they do so, then at the point of intersection there will be two tangents. It means that there are two directions of electric field, or there are two values of electric field at that point, which is not possible. Sixth point, electric field lines of force are closer when the field is stronger, and the lines are spread where the electric field is weaker. You can see that from the adjacent figure. Now the seventh point, electric field lines of force are always perpendicular to the surface of a positively or negatively charged body. If I take a conducting body, a conductor, electric field lines are always perpendicular. So that is what you are seeing on the two figures. The first figure is actually a rectangular shaped body, and second figure is an irregular shape. So whether it is a regularly shaped or irregularly shaped, the electric field lines are always perpendicular. And one more thing you can notice from this figure is that no field lines are passing inside the conductor. That means inside the conductor electric field is 0. So please remember, you should not draw any electric field lines inside the conductor, because inside the conductor electric field is 0. Now 8th and 9th point we have already discussed. If there are two unlike charges, that means positive and negative charges, electric lines of force will contract lengthwise to represent the attraction between two unlike charge. And electric lines of force exert lateral pressure, which means sideward pressure, to represent the repulsion between two like charges. The 8th point and 9th point is represented in the previous figure that I will show you. Look at the figure on the left side. This is due to two unlike charges. So the field lines are getting attracted. That is why we call they contract lengthwise. This is the contraction towards lengthwise. Now look at the figure on the right side. There you can see two like charges. There the lines of force exert lateral pressure. That means which shows the repulsive force. Okay. Now, so there are 10 properties. There are 10 properties given. You don't have to write all those properties. I'll just tell you which all points are important. You need to write only those points for the exam. Point number 3, 4, 5, 6 and 7. 3, 4, 5, 6 and 7. You just need to write only those points at the time of exam. The remaining points are just for your understanding. Now, if I am taking a conductor like this, a thin conductor, and charge this conductor, you can see that the charge will be uniformly distributed along the entire length of the conductor. If I take a thin conductor and charge it, the charge will be uniformly distributed along the length of the conductor. So, we are going to discuss now uniform charge distribution. Uniform charge distribution. The first one is called linear charge distribution. In linear charge distribution, as I told you, if I take a straight conductor and charge it, the charge will be distributed along the length of the conductor. So, I can write like this: lambda is equal to Q by L, charge by length. Lambda is called linear charge density. Linear charge density. And SI unit of lambda is Q by L, which means Q is coulomb, L is length. So coulomb per meter. Now the second type of charge distribution is surface charge distribution. Surface charge distribution. Instead of taking a conductor like this, just imagine we are taking a sheet of paper and charge the sheet of paper. The charge will be distributed on the overall surface of the paper. Okay, so if we take any metal sheet like a thin sheet of paper and charge it, the charge will be uniformly distributed along the surface, and such kind of distribution is called surface charge distribution. And we can write surface charge density as sigma. Sigma is equal to Q by A. Q is the charge and A is the surface area. Sigma is called surface charge density. Now, how will I find the SI unit of sigma? SI unit of sigma, Q by A, charge, coulomb, and area, meter square. So, I can write coulomb per meter square. Now, the third type of distribution is volume charge distribution. Imagine a block like this book. It is having a definite volume. So if I take an object like this which is having a certain volume and give the charge will be uniformly distributed throughout the volume of the body. So if the body is having a three-dimensional space, a volume, and if we charge the body, the charge will be uniformly distributed overall the volume of the body. Such kind of distribution is called volume charge distribution. So I can write volume charge density as rho, which is charge by unit volume, where rho is called volume charge density. SI unit of rho is coulomb per meter cube. Thank you.